Hello everyone, my name is Veerapawan Kumar Sirapu and today I'll be presenting my project on predicting loan default using linear and nonlinear machine learning models enhanced with SHAP interpretability. So this work compares how different model types perform, how well they generalize and importantly, how transparent they are when making credit related decisions. So, the loan default prediction plays a major role in credit risk management because lending institutions depend heavily on accurate assessments of borrower risk. So, the traditional linear models like logistic regression are widely used because they are simple, efficient, and easy to interpret. But the challenge is that borrowing behavior is often complex and nonlinear and linear models struggle to fully capture those patterns. On the other hand, nonlinear machine learning models can learn richer relationships and usually give better predictions, but they suffer from a lack of transparency, which becomes a regulatory concern in finance. So, the motivation behind this project is to find a balance, a way to get that strong predictive accuracy while still maintaining the interpretability needed for the real world financial decisions. So, when I reviewed the existing studies, I noticed a clear pattern. Most research mainly focuses on improving accuracy, but very little addresses interpretability. Very few studies use tools like SHAP to explain the reasoning behind model predictions. There are also a lack of comprehensive comparison between linear and nonlinear models across accuracy, interpretability, and computational cost. This gap is important to address because financial organizations cannot adopt black box models unless they can justify and explain this prediction. To close these gaps, I focused on three main research questions. Firstly, how do linear and nonlinear models differ in predictive accuracy and interpretability for loan default prediction? Secondly, how can SHAP help us understand how each model arrives at a prediction? And thirdly, what trade-offs appear when we compare accuracy, interpretability, and computational efficiency across these different models? So, these questions led to five main objectives. I began by selecting representing models from both categories. Then I evaluated them using accuracy, precision, recall, F1 score, and AUC. Since the dataset was highly imbalanced, using SMOT was necessary to train fair models. And then I applied SHAP to get both global and individual explanations of the model's predictions. Finally, I compared the models in terms of performance, interpretability, and computation time to understand the trade-offs clearly. So, the dataset contains demographic, employment, financial, and credit information from borrowers. The target variable was extremely imbalanced, with only about 2% of borrowers in default. To prepare the data, I checked for missing values, label encoded categorical fields, and standardized numerical features like income, loan amount, and credit score. I used a stratified 80 by 20 split so both training and testing sets reflected the real default ratio. So the smooth oversampling was applied only to the training data so the models could learn the characteristics of defaulting borrowers. So in this slide, the workflow followed a structured pipeline. I started with the data exploration and pre-processing and then applied smooth to address imbalance. Next, I trained three models: logistic regression, random forest, and gradient boosting. Their performance was evaluated using multiple metrics, and then sharp analysis helped interpret how each model was making decisions. Finally, I compared these models to identify the strengths, weakness, and practical considerations. Moving on to the next slide, there's a here's a closer look. Three models. Logistic regression serves transparent baseline that fast and easy to interpret, but it can't capture but it can't capture complex and non-linearity. So, the random forest is an ensemble of decision trees that captures feature interactions and more effectively and tends to be more flexible. So, in the gradient boosting, it builds models sequentially and usually achieves the strongest predictive performance, although it requires more computation. So, these models represent three different levels of complexity and interpretability, which makes the comparison meaningful. Overall, so in the next slide, when looking at the results, gradient boosting consistently achieved the strongest F1 score and the highest AUC. Random forest performed well overall and provided a good balance between accuracy and resource usage. Logistic regression delivered the fastest training time and full interpretability, but had weaker predictive performance. And SMOT played a major role after balancing the data. All models showed dramatically better recall and F1 scores. In terms of computation, logistic regression was fastest, followed by random forest and gradient boosting the longest. So, in the next slide, before applying SMOT, the models struggled to detect defaults cause the dataset was dominated by non-default cases. Accuracy is high, but recall was very low, especially for identifying true defaults. This is a classical issue with imbalanced datasets and shows why balancing is essential. So in this next slide, performance with SMOT, the models finally learned what default cases looks like. So the recall was improved dramatically, meaning the models were now able to flag risky borrowers more accurately. Although false positives increase slightly, this trade-off is typically acceptable in financial risk management. Moving on to the next slide, this comparison clearly shows uh, how imbalance affects performance. Without SMOT, all three models acted too safely and predicted the majority classes. So with SMOT, precision, recall, and F1 rose across the board, and the models behaved more realistically. This highlights why data balancing is just as important as model selection. So, moving on to the next slide, a deeper look shows important behavior differences. Logistic regression relied mostly on simple linear signals and missed subtle interaction. Random forest captured many small interactions but occasionally misinterpreted borderline borrowers. And the gradient boosting handled nuanced relationships the best and produced the most consistent predictions across the dataset. So, moving on to the next slide, the architecture, comparison, and trade offs. The overall gradient boosting provides the strongest predictive performance. Regression remains the most interpretable and fastest. Random forest sits in the middle, offering a good mix of accuracy and interpretability. The key message is that SHAP helps reduce the interpretability gap by opening up the reasoning behind nonlinear models. Ultimately, choosing a model depends on whether the priority is accuracy, transparency, or speed. In this plot, the SHAP played a major role in understanding how the models think. The SHAP summary plot showed the features like age, income, interest rate, credit score, and months employed were the strongest contributions to predictions. Logistic regression produced clear linear explanations, while random forest and gradient boosting offered more complex but richer insights. SHAP allowed us to trust and verify the decisions of the nonlinear models. So, in this slide, key search findings are there are several takeaways from the findings. Firstly, nonlinear models do outperform linear ones in predictive accuracy. Secondly, SHAP provides reliable explanations for both model types. Thirdly, the strongest predictors were consistent across models. Fourthly, smooth was absolutely essential for meaningful default decisions. And finally, even complex ensemble models can be made regulator friendly when SHAP is integrated. So in this slide, the solutions for the research questions are, so based on these findings, directly answer the three research questions. Nonlinear models give better accuracy while linear models remain easier to interpret. And SHAP provides SHAP bridges the gap between by clearly explaining how features push predictions up or down. Sorry. And each model carries traits of gradient boosting, excels in accuracy, but is computationally expensive. Logistic regression excels in transparency, and random forest offers balance. So, in the conclusion, this study shows that nonlinear models provide superior predictive performance for loan default forecasting. But interpretability is equally important, and SHAP enables us to understand even complex models with ease. The framework developed here brings together performance, interpretability, and efficiency, three essentials for deploying machine learning responsibly in finance. Sorry, future work. There are several ways this work can be expanded. Adding macroeconomic variables could be make the models more realistic. Testing advanced algorithms like XGBoost and CatBoost may improve the accuracy further. Evaluating fairness across demographic groups would support ethical lending practices, and SHAP dashboards could give the loan officers real-time, transparent, and decision support. So, in the final takeaway, the key message is simple. We don't have to choose between accuracy and transparency. With SHAP, even the most powerful and nonlinear models can become explainable and trustworthy. Now, moving on to the coding section. So, in this coding section, in the first part of the code, I imported all the necessary libraries for data processing, model evaluation, and SHAP interpretability. And also, I also included a quick check to see whether a GPU was available. This isn't required for classical machine learning models, but it's a good practice because certain SHAP computations can benefit from the GPU support. Next, the loading and inspecting the dataset. Next, by using pandas. I inspected the first few rows, checked the shape of the dataset, looked for the missing values, and reviewed the sorry and reviewed the summary statistics. This step helped me to understand the structure of the data and confirm that the default variable was highly imbalanced, with a very few borrowers marked as defaulters. I also created a simple count plot to visualize this imbalance. This became the more important later when applying smooth. So after I removed loan ID column because it doesn't provide any predictive value, then I applied label encoding to all categorical features such as education, employment type, marital status, and cosigner status. This step converts text values into numerical values because machine learning models cannot work with raw string labels. And and after that, I separated the dataset into feature and target variable, and then performed a stratified 80 by 20 train test split. Stratification ensures that proportion of defaulters stays consistent in both the sets. After this, I strategized The numerical features like income, loan, and strategized income, loan, and amount, credit score, and DTI ratio. So, scaling matters especially for models like logistic regression and gradient boosting, and which are sensitive for feature magnitude. Before balancing that data, I trained all three models logistic regression, random forest, and gradient boosting on the original imbalance set. For each model, I recorded training time, prediction time, and performance metrics. I also generated classification reports on confusion matrices. As expected, all models showed up very high accuracy, but extremely low recall for default class, meaning they almost never predicted actual default tests correctly. So this reinforced the need for smooth. After applying smooth, after observing the imbalance issue, I applied smooth to oversample the minority class. Smooth creates synthetic default samples so that the model learns the characteristics of defaulters more effectively. I retrained all three models using balanced dataset and evaluated their performance again. So this time I recall F1 scores improved significantly for all the models, which means they become much better at recognizing borrowers who are at risk. Comparing, I created a F1 score comparison charts on ROC curves to visualize how smooth change the model performance. These comparisons clearly showed that balancing the dataset is crucial for credit risk modeling because accuracy alone can be misleading when the target class is here rare. So I used SHAP to explain how both logistic and random forest made their predictions. For logistic regression, the sharp summary plot showed the features like age, cosine status, and interest rate dependence, mortgage, and income had the highest influence. uh, highest influence on the predictions. Younger age and higher interest rates pushed the model towards predicting default, which higher income and longer employment history lowered the predicted risk. This gave us a clear picture of how the model uses the feature. So, for a random forest, I used a tree explainer version of SHAP. I extracted the SHAP value for class 1, meaning the model's predictor for default. Key predictions included age, interest rate, has cosigner status, income, once employed on a loan amount. SHAP confirmed that the model was learning meaningful financial behaviors rather than random noise. So by making the nonlinear models more trustworthy. Local SHAP explanations. So then then I selected in the local SHAP explanations, I selected a single borrower and generated a local explanation for both models. This showed how each feature pushed that individual prediction upward or downward. For example, a high income might reduce risk, while a short employment history might increase it. So, the local explanations are extremely valuable in real world lending because they allow loan officers to justify individual decisions. Thank you.